All right, so second half of chapter 9 here. Where we left off was talking about electrons and how we figure out which orbital they're in. Actually, let me go look back a little farther than this and we can do a little more recap because we kind of covered a lot of stuff. We'll start let's start here, or actually this one. Okay, so we have these orbitals ending with an AL. We talked about orbits. Those are specific paths, like a planet or like a moon around a planet or the planets around the sun. Follows the same path every single time. We learned that electrons don't do that. They instead exist in these like nebulous clouds where they're very likely to be, but not 100% likely to be. Electrons are spooky like that. This is the lowest energy orbital. It's the 1s. It's the sphere. If you move up in energy, which correlates to moving down on the periodic table, every s orbital gets a little bit bigger, but they're all spheres. And then we note which energy level by n equals 1, n equals 2. So here, the 1s orbital, that's n equals 1 s orbital. The 2s orbital is n equals 2, an s orbital. So if you go up to n equals 3, it would be 3s. We also learned about the p orbitals, which are the dumbbell-shaped orbitals. Like the s orbitals, we name them with the n level, the energy level, principal energy or principal shell number, and then the letter, which tells us which type of orbital. So the p orbitals, there's 3 of them. Each one shaped like a dumbbell in a different direction. Well, here's the subshells again. So if you have, for every level of n, you have that many orbitals, up to 4. Over here, oh, this slide. So we also talked about the d level orbitals. And again, they're labeled first by whichever energy level they're in. So the smallest d orbital is 3d, and every d orbital at higher energy levels gets a little bit bigger, but it's the same shape, which was this drawing right here with just the s and p orbitals, s orbitals being these circles, and then the p orbitals being these sort of overlapping dumbbell shapes on top of it. So all of these things are kind of stacked and mushed on top of each other to fill in, really, all of the space around an atom or a nucleus. So these are the d orbitals. They have sort of cross shape in every conceivable direction, and then a dumbbell and the donut. Again, every one of them gets larger as you go up in energy levels, increasing this number in front. So we've got all these orbitals now, and then we looked at how do we tell which orbitals the electrons are in. So we use electron configurations to tell us that. And really, they just fill in from the lowest energy to the highest energy orbitals, kind of like filling a cup with water, except if the water could only be at certain levels in the cup. So actually, let me go back to this. So here, again, we have the 1 indicating that n equals 1, that we have an s orbital, and that we have 1 electron in that orbital. And we also did orbital diagrams where we used arrows to indicate the spin of the electron, because the Pauli exclusion principle states that we can only have 2 electrons with opposing spins. So one has to be a little half up arrow, and the other one's a little half down arrow. Can't have 2 arrows going in the same direction. So when we write these out, we figure out how many electrons each atom has. So helium has 2 electrons. We know that because when we look at the periodic table, look at the periodic table here, helium So the atomic number is the number of protons. That is also the number of electrons that an atom has when it's neutral. Same number of protons and electrons. So helium has 2 electrons. So if we go back to this guy, we can see we have 2 electrons. And so we start with the lowest energy orbital, 1, and then the first orbital in that energy level is S, and we put both of those electrons in there. In an orbital diagram, we then write that half up, half down arrow, and we say that this box is 1s. So get a little bit more complicated with lithium. Lithium's atomic number is 3, has 3 electrons. So 2 electrons go into 1s. 1 electron goes into 2s. If we were to write out all of the orbitals from 1 to 5s, or really 4d because it's the highest energy level there, this is what it looks like. And so if we were to fill in for any of these atoms, for any atom, up to however many electrons that is at 4d, we'd start from the bottom, fill in the lowest energy ones first, moving up to higher and higher energy, just putting 2 electrons on each of those lines. Do you have a question? Oh, no. So the other rule that we covered is Hund's rule. When filling orbitals of equal energy, we fill singly first. This is like Mrs. K's Chemistry Land Hotel, where the electrons don't want to share beds. So they get 1 into each bed first, and then if they have to, they double up. So here we see with oxygen, we have 8 electrons. And again, if we go to the periodic table, you can see that oxygen's atomic number, that number at the top left, is 8. 8 protons, 8 electrons. For neutral oxygen, I won't ask you to do, actually I won't say that yet. Might ask you to do atoms with different charges, but we'll cover that. Doing so good. So this was a trick for remembering how to fill orbitals. It gets a little bit tricky once you get to n equals 3 or n equals 4, because we fill 4. Yeah, we fill 4s before 3d. So again, this is just writing out all of these. So we write out 1s, 2s, 3s, 4s, for example. And then p starts at, we have p orbitals at n equals 2, 2p, 3p, 4p, and then it goes 3d, 4d. And then we fill these orbitals on a diagonal in terms of the order. So we start first with 1s, then 2s, then 2p, then 3s, then 3p, then 4s, 3d, and then 4p. So that's kind of how that works. You can also use the periodic table as a guide, as long as you remember that, again, once we get to n equals 4, that n energy level corresponds to each row of the periodic table. So this is n equals 1. This is n equals 2, n equals 3, n equals 4. And again, when we get to n equals 4, we have, it's even written on here, 4s1, 4s2, and then scandium is 4s2, 3d1. So that d orbital that we fill is actually in the n equals 3 principal quantum shell. So to double summarize our summary, the lower energy orbitals fill before higher energy orbitals. Orbitals can hold no more than 2 electrons each, and they have to have opposite spins. When orbitals of identical energy are available, so something like 2p, we would fill those in with singly first, so 1 in each orbital, and with the same spin. rather than pairing anything up. So I believe the last thing that we left off on was writing out these electron configurations for atoms with more electrons. And I did lead as an example. So when you get farther down the periodic table, remember the atomic number is the number of electrons. So if you have to do something like 50, you have to put 50 electrons each in their place, which can take a while. So chemists have developed shortcuts for writing those electron orbital diagrams. But I think that's coming up on the next slide or two. All right, so now we're on to new stuff.
May I have your attention, please? This is Atlas IED.
So for sodium, right, oh yeah, I was right. The electron configuration of the previous noble gas, so it's the noble gas on the line above it, can be abbreviated. The electron configuration for the previous noble gas can be abbreviated by the symbol for the noble gas in brackets. So we're looking for sodium, Na. So we go to our periodic table, we can see sodium over here, 11 electrons. And while that's a far cry from 50 or 82, we can still shorten that. On an exam, I might ask you to write out the short, I might give you no restrictions and say just write out the electron configuration, in which case you can use a shortcut. But if I say write out the complete electron configuration, I'll try to remember to say do not use a shortcut. I do want to see the whole thing. But for sodium here, you see sodium is on the third row, so it's N equals 3. But if we wanted to abbreviate this, we would go to the row above it, and then all the way over to our noble gas, neon. So we could abbreviate our electron configuration for sodium and say, okay, we're going to start with neon in square brackets. And then go back over to a periodic table just to show this. So sodium here, how many electrons more than neon does sodium have? Just one. All right, so you could figure that out by doing 11 minus 10, the atomic numbers. But we have one more electron. So we're going to place that one electron in the first available orbital, which is going to be 3, because we're in the third row. And its s is the first orbital. And it'll be 3s1. So neon, and then 3s1. One of the things I didn't cover in my recap is that we have these different sections of the periodic table. These columns 1 and 2 are called the S block because each of the atoms or each of the elements here has its highest energy electron in the s orbital. For the elements on this side, this is the p block. They all have their highest energy electron, the last placed electron, in a p orbital. And all of the elements in the middle here are the d block because they have their highest energy electron in a d orbital. So that is kind of a shortcut that you can use to figure out these electron configurations. Okay, so that's sodium. We just abbreviated with neon in brackets, 3s1. All right, so if we want to do aluminum, find aluminum on the periodic table. It's over here, 13. Which noble gas would we use to abbreviate our electron configuration for neon, or aluminum? Neon, right? So we just go to the row above and find the noble gas at the end. So we'll start with neon. Really need to do shortcuts here. And then aluminum, well, I'll just tell you this. Aluminum is element number 13. Neon is 10. So how many more electrons than neon do we have? 3. So what orbital are we going to fill first? S. And what principal? We're in the third row of the periodic table. So it's 3s. How many electrons? We have 3 electrons, but we can only put 2 in the s orbital. So 3s2. And then what comes after 3s2? 3p1. Because we have 1 more electron left over. Just to kind of show you on the periodic table, what you could use as a shortcut is you could say, okay, so aluminum's here. That's the first element in the p block. It's going to have 1 electron in the p block. And coming before it are 2 elements in the s block. So it'll have 2 electrons there. Yes?
I have a question. So why are you using neon? Is it because it's the closest?
It's the closest noble gas.
But isn't like the whole like Ag and then, or like helium and then argon and that whole row, isn't that like noble gas? Wouldn't you just use, or is it because you're going up and then
You have to go to the row above.
above and then?
Yeah.
Okay.
Because, yeah, we don't have a way for writing. I see what you're saying, because we could do argon maybe.
Yeah.
So let me, if we wanted to do sulfur, then we would say, oh, well, argon's closer. But then you have to write argon, and then you'd have to do minus 2p2 or 3? Minus 2? No, be minus 2p2. It gets weird. So basically, we always are adding electrons onto one of the noble gases.
So you go up the row and then to
And then to the end.
noble gas. Okay.
Yeah. So if we wanted to do sulfur, we would still use neon.
Yeah.
And then we would do 3s2, 3p4 for sulfur. Yeah.
Would it be 3s based on the row it's in, or?
Yes. Yeah, so the row also tells you that it's going to be 3s for aluminum, silicon, I mean everything in the third row. And actually for the d orbitals in here, the d block elements, their highest would be 1 minus, or would be the 4 minus 1. Because the highest energy d orbital here is 3. Okay, so let's do bromine now. I guess we've got to go right back to the periodic table. Bromine is number 35. And I'll be giving you a periodic table for the exam. The periodic table will be pretty much exactly like this one, with the names and the elements. So for nomenclature, you have these names available to you. So bromine does have 35 electrons, but we're going to abbreviate that. So what noble gas are we going to use?
Argon.
Argon. Yes. We always go back a row. It's not the closest noble gas. It's the noble gas at the end of the row above it. So we're going to use argon. So we'll start with abbreviation here. And then bromine is element 35, and argon is 18. So bromine is 35, argon is 18. So how many more electrons does bromine have? Did I write that wrong? Oh, yeah. Because it has d orbitals. I was like, I was expecting 7. You'll see why I was expecting 7 later. But you're right, 17. So starting with, move this over a bit. Starting with 4 S2. So pretty much if it's past the S block, it's always going to be 4s2, 3s2, right? That's going to be filled. Then what comes next? And actually, let me go back to the periodic table. So we're 4s. Yeah, 3d comes next. Because we're in the 4 So then the next one is D, the D block, and that's 3D. 3D, and then there are, should we go back to this? If you want to count all the way across there, there's 10 elements across the D block. So it's going to be 3D10. D block does some weird stuff. So 3D10. And then how many are we going to have in the P block? Before P, I think I heard somebody say it, right? Or not that. 5. So that's the 17 electrons difference between bromine and argon. Yes?
So why are you using D and why is it 3? It's 3 because it's in the third row, correct? Because you're going...
It's, yes, I know. I remember I was confused by 3D. I always forgot that it was 3D. Maybe you just remember it's like a 3D movie, 3D, I don't know. I guess maybe augmented reality is more relatable now. Okay, so it just has to do with the energy levels of each of the orbitals. So you can see that 3D actually is higher in energy than 4s. So at this point, well, and then this is the first time that we've added the d orbitals. And because of more advanced chemistry reasons, it starts at 3.
And 3D can carry more electrons?
Is what? Oh, more electrons? Yeah. Yeah, it can hold a lot of electrons.
Do you know how many? Well, I know after, right, it could only hold up 10, right?
Mm-hmm.
Is that true? And then that's why we switched to P. And can P hold up to 2? Or you put 5, but can it hold up to 10?
P can hold 6.
6, okay.
Yeah, so there's 3 spots here. That's 2 when if I go back a little bit farther. These are the 3. These represent each of those 3, or those 3 lines, I should say, represent each of these orbitals. So one of them is in like px, one of them's in py, and then pz. Yeah.
How can you tell how much each orbital holds? So like, I know you were saying that P holds 6.
Right.
Is that just something we have to like memorize, or is there like something that you could just like, look at?
Looking at the periodic table, actually, you can tell. If I want to get to this periodic table. So you can see that there's, like, each of these would have 1 in the s, and each of them would have 2 in the s. So the s orbital can hold 2 electrons. Here, there's 10 elements in the d block. I got off there a little bit, but 10 elements in the d block. So you can have 10 electrons in each d orbital.
Got it.
And then for p, there's 6 elements across. So that's 1 electron for each of those. There's 6 in the p orbitals. Yeah. Good? So, and actually, let me, just real quick. The way I like to do these is I just use the periodic table. So if I wanted to do, erase carbon here. Let's do bromine again. So we're going to do bromine. Then we're going to start with argon again, because we want to make this a little easier. And then I would look at that row that bromine is in, right? So we got bromine right here. And I would say, 4s1, 4s2. 4s2, and then 3d1, 3d2, 3d3, 4, 5, 6, 7, 8, 9, 10. And really, you don't have to count all of those. You know that there's going to be 10 there, so you can say, okay, we're past the d block even, so that's 3d10. And then 4p1, 4p2, 4p3, 4p4, 4p5. So really, the electron configuration represents every single element. So you can just kind of count them. Yeah?
So when you said 4s2, so that would be 3d1, or it's going to be either one? Yes.
That is 4s2, 3d1. And then these ones are all 4s2, 3d10, 4p1, 2, 3, 4, 5, 6. So they didn't put it all in there because that would be too long. It doesn't fit in the box.
So it's all 4s2, it's just the ends just be different.
Yes.
So there's 31.
Because for every element, you're adding one more electron.
And then the top one would be like 3s. Like above 4s would be 3s, correct?
Yeah. Yeah, so this would be 3s1, 3s2. So if you wanted to do aluminum, you could abbreviate with neon, and then say it's 3s1, 3s2, and aluminum is 3s2, 3p1. Yeah.
So all like all the light blue boxes are S, and all the brown ones are D.
Yep. And the pink ones are, yeah. Well, I guess they're horribly colored. The ones on the right are supposed to be pink. Uh-huh.
For chromium, it says 4s1. Is that just an error, or is
No. Chromium is weird. Well, the d orbitals are weird. So it's better to have 5. So if you think about what's happening is there's, not like that. So if this is 4s, and then this is 3d, what's happening with chromium is that it's 4s1, and then you can have, keep bumping the thing, 1, 2, 3, 4, 5. So having all 5 of those filled with parallel spins is actually lower energy than if one of those was in 4s. You'll see the same thing that happens with copper. So it's 4s1, 3d10. So one of those s electrons has jumped into the 3d so that it can be completely filled, which are just quirks. Like, I'm not going to put those ones on an exam for exactly that reason.
yeah?
They're weird exceptions. I think they're cool, but
And then what about 41? Why is there 45s?
which one?
41.
Oh, niobium. Again, it probably has to do with a similar, more stable, just happens to be that way. Yeah.
So for helium, right? Would it
Uh-huh.
it would just be 1s2, not even a p in it,
Right.
just 1s2.
Yeah, so helium's the one that kind of breaks it. You can't have any p orbitals because we only have 2 electrons. So helium is a little bit weird.
So just classify that as 1s2.
Yeah. The rest of the periodic table very neatly follows the pattern. Good? This is going to be really important because it explains a lot of things. So I don't mind spending some time on this. Okay. Let's go back over here then. All right, so we did bromine. Now we can do strontium. So strontium, all the way down over here. Almost sneezed. Okay, so strontium, if we want to abbreviate this, what noble gas would we use? Krypton. Superman's weakness. Oops. Okay, so Kr. Now, what is our electron configuration for strontium going to be after that? So if we started with krypton over here, we just have 2 more electrons. 5s2. That's all there is to that one. And again, if you wanted to, you could do the fact that strontium is 38 and krypton was 36, right? Yeah, 36. And you could say that there's 2 more electrons there that we have to fill in. Or you could just look at the periodic table and see, oh, strontium is in the 2nd column on the 5th row, so it's going to be 5s2.
So like, yeah, okay, so if it's just like only like just 2 electrons, it would just be like either 4s2 or like 5s2, just in that
Yeah. Well, yeah, so really for anything in that 2nd column, their highest energy electrons will be 4s2 or 3s2 or 2s2. D is the only place it gets a little tricky, and we're not even going to talk about F. Just there's an F. Like, we're not going to talk about it. Okay, so let's write an orbital diagram for argon. Really need to get away to, I need to have both of these up. So we want to write the orbital diagram for argon. Again, there's a couple ways that we could do this. You could consider each row, you could just count the electrons and fill them in. I think the most consistent way is to just count electrons and fill them in. So for start, we got to start over with hydrogen, and then we'll work our way down until we get to argon. What will argon's highest energy electron be, though, based on where it is on the periodic table? It'll be P. But even more specifically, what principal energy shell will be 1p, 2p, 3p? It'll be 3p, and the very highest energy electron will be 3p6, because the last element is the sixth element in the p block. So just at a glance on the periodic table, you can do that kind of thing. All right, so our first orbital, if we're starting without any abbreviations, is going to be 1s. And we've got 18 electrons to fill in here. So it'll be 1s2. And then we'll go to 2s2. Then 2p6. Then what's next? 3, not P, S. We always fill S first, and then P, and then when we get to D orbitals, only at the fourth row do we start filling in D. So it'll be 3s2, 3p, 6. Oh, sorry, this is the electron configuration. So our orbital diagram has to have things written out like this. So for each of these, we're going to have a set of orbitals. So it'll be 1s, 2s, 2p, 3s, 3p. And you can write those as just lines. Just make sure they look like they're grouped together, or you can write them as boxes. And then you can really group together things like the p orbitals. So writing out an electron configuration can help you write out the orbital diagram, because it already tells you how many of those orbitals you need to write or draw out. And then we just fill all of these in with electrons according to our electron configuration. So this 2p6 is going to get 1, 2, 3, 4, 5, 6. 3s gets 2. And then 3p will get 6. So we're only filling in all 6 because we have all 6 filled in our electron configuration, which we got from the periodic table. Yeah.
When you mean we're filling in all 6, are you talking about, like, for the orbital, are you talking about just those for the 3p?
Yeah, all 6 electrons in 3p.
Okay.
So if this was not argon, but would it be fluorine? No. Bromine? Chlorine. It'd be chlorine. This would be 3p5 for chlorine, and then we'd only put 5 electrons in here. So you'd have one that's unpaired.
So like, would each like box be like 2?
Yeah.
Okay.
Yeah, so that's why I wrote one as like the half up and one as the half down arrows.
Okay.
Yeah.
Say on the exam you give us a question like this, could we write it either way? Like could we either do like little arrows for the numbers, or do you just want the numbers?
It'd be two different things. Yeah, so if I ask you for an orbital diagram, this is an orbital diagram. If it was just the numbers, this is an electron configuration. So they're two separate things. And I wouldn't ask you for an orbital diagram of lead without taking shortcuts. If you can do it, you can do it. Are there any other questions from anywhere other than the second or the first and second row? Well, there's nobody in the very first row. Okay, that's fine too. Okay, so why is this all important? Well, valence electrons, they're the valence, the vanguard, all these words mean like the front line. Valorant, that's what I was thinking of. Valorant's different, but sorry, getting sidetracked. Vanguard is Valorant's anti-cheat. Valence electrons are the highest energy. They're the front, they're the edge of each atom. So when atoms bump up against other atoms, it's the valence electrons that are interacting. So these electrons in the outermost principal shell, is what we talked about for all of these things, whatever row it's in, that's its highest energy principal shell. Those are also, just the electrons in that row are its valence electrons. So again, these are involved in chemical bonding. They involve all the interactions. They explain a lot of why atoms behave the way they do. The other electrons are core electrons. So these are the key terms here I would like you to remember. Valence electrons, specifically that these are the outermost principal shell. The electrons that are not are the core electrons. Okay. So when we're looking at an electron configuration for something like silicon, only these are valence electrons. They're the highest energy principal quantum shell. It's because they have that 3 highest energy, those are valence electrons. The rest of those are core electrons. If you look at a periodic table as well, see silicon is right here. See, I need a way to flip back and forth more quickly. So we've got 3s2, 3p2. If we look at the periodic table again, these are sort of accounting for 3s2 and 3p2. So it's got 4 valence electrons. It's 4 elements into the periodic table. The rest of them are all core electrons, and that's also why we can kind of just abbreviate them with neon. All right, so if we want to write an electron configuration for chlorine, chlorine is element 17. So let's do this just using the periodic table. The first row of core electrons is this first row, so it's going to be 1s2. Then we move down to the second row. We have 2s2. And then this is 2p6, because we fill all of those in. That gets us up to neon, which is also 10 of our electrons that we've used up. And then 3, we'll have 3s2. And then we are 1, 2, 3, 4, 5 into the p block. So our highest energy is going to be 3p 5. Again, this is always following the same pattern. So if we wanted to write this out here, we'd still start with 1s2, 2s2, 2p6, 3s2, 3p5. Having like flashbacks of just like writing these out over and over and over again. So you can practice this for any element on the periodic table. Just pick one, write out the electron configuration. It'll take a while, but it's good practice. So what are our valence electrons for chlorine? 3s and 3p, yeah. So these ones that are in our n equals 3, whoops, principal quantum shell. So the number in front of the letter is the principal quantum shell. Those are our valence electrons. All right. So again, looking at the periodic table, you can tell how many valence electrons something has based on what column it's in. So elements in column 1 have a single valence electron. Elements in column 2 have 2, and 3, and so on. Right? So chlorine over here is in column 7a. So it has 7 valence electrons. That's part of why the periodic, well, actually, I think that is why the periodic table is broken down into this 1 through 8a, rather than counting all of the D block. The D block electrons, I don't think are ever valence electrons. So you can tell how many valence electrons based on the column. So the number of valence electrons for any main group element, except helium, is equal to the group number of its column. Again, doesn't work for helium because helium is a noble gas, so it's over on top of the noble gases. But really, its number of valence electrons is 2. So these are all main group elements. I know that's actually going back a bit. So the main group elements are columns 1 and 2 are S block, and columns 13 through 18, which is the P block. Those are all main group elements. These in between are transition metals. So then the row in each, or the row number is the principal shell, the highest principal shell. I guess versus the periodic table again. So, right, it's easy then to pick out something, silicon. Say, okay, well, silicon's in 4a, so it has 4 valence electrons. Nitrogen's in 5a, it has 5 valence electrons. So the transition series, again, that's these in the middle. Those represent the filling of core orbitals. So remember, our valence electrons are the highest principal quantum shell, and D is always 1 less than the row. So if we were to do, how many valence electrons does selenium have? You skip all of the d orbitals, or all the d electrons, because those are all core electrons, because they are 3d, whereas the s and p block orbitals, or electrons, are 4s and 4p for selenium. So it still has 6 valence electrons, because it's in column 6A. Oops. So those are, so D and F, they are core orbitals. So the number of valence electrons is mostly constant. And then this is where he asked about copper. I don't remember what the other one was. What was it? Chromium. Copper and chromium have the half-filled and completely filled d subshells, which are special cases for d orbitals. So if our valence electrons are in the highest principal quantum shell, valence electrons are the highest principal quantum shell, so d orbitals can never be valence electrons. Always core electrons. Feel free to ask me for clarification if my handwriting is ever not neat enough. This is me trying to be neat. It's rough. As soon as I get my PhD, it'll get worse. Right, so again, all of our outer electrons. As we look in here, let's look at scandium in particular. So for scandium, it's only got 2 valence electrons because this 3d1, that 1 electron is in a d orbital. And that's 3d, which is less than 4d. So those are just core electrons. All right. So if we write out the electron configuration for phosphorus, what we're actually doing when we use neon as an abbreviation is we're saying this represents all of the core electrons. So we're not super concerned with those. So for phosphorus, we would start with neon, and then we would have 3s2, 3p3. So those are inner electrons. So I guess I kind of showed you this already, but you can write the electron configuration for any element based on just where it is on the periodic table. You use the symbol for the previous noble gas in brackets. That represents core electrons. Your valence electrons, or outer electrons, are determined from the element's position within a particular block. So you find its row. That'll be the number that goes in front of your valence electrons. And you figure out where it is in the block, and that's how many electrons it has in whatever block it's in. All right, so just from the periodic table, do the electron configuration for tin, which I don't know why this periodic table is here because it's got the answer right there. So for just the valence electrons, we could start with the noble gas and the row above. So if we go up a row and then to the end, we'll use krypton as our core electrons. And then we would write, what row is it in? It's in row 5. So it would be 5s2, and then our 4d10, and then 5s, and it's in the second column of the p block. So it'd be 5s, sorry, 5p2, not 5s. We already did 5s. Good. Any questions? Yes?
I have a question on how we got the 5s2. Is that because it was in the fifth row,
Mm-hmm.
and then s, we didn't start with 5s, because it can only be, it can hold 2 electrons, right? So that's why we put 2?
Yeah.
Okay.
And we know that those are filled because it's farther down the periodic table. So this would be 1 electron, 2 electrons, and then the 10d electrons, and then 1 and 2 more electrons that go in the p block. Either one.
So it goes from S, D to P because of the like the structure that you wrote out for us, and it goes like diagonally, right? Like
Yes, and that's why it goes from 5s to 4d, and then back up to 5p. So the d orbitals are always 1 less than the row number. So if we did, instead of tin, if we did 32 here, which is germanium, this would be 4s1, 4s2, 3d, 10, 4p1, 4p2. So it would end with 4p2. You don't have to write out 4p1 and then 4p2. That was your question too? Okay. Cool. All right. So as I mentioned before, the chemical properties of elements are largely determined by the number of valence electrons they contain. So element properties vary in a periodic fashion because the number of valence electrons is periodic. So I mentioned this a few times, but on the periodic table, if you look at a column, they all have similar properties. That's because they have the same number of valence electrons. So the noble gases are all inert, they don't react with anything, because they have 8 valence electrons, which is a magic number for elements, we'll find. All of these are reactive, the alkaline metals, because they have 1 electron in their valence. They have 1 valence electron. These are reactive, but a little less reactive, because they have 2 electrons each in their valence shell. So this is part of the quantum mechanical model, and it explains the reactivity of hydrogen and all of those other alkaline metals, but also the inertness of the noble gases. So atoms with 8 valence electrons, or 2 for helium. Again, 2 is kind of a weird exception because it's so small. But if you have a full valence shell, which is 8 electrons, right? That's all the way across the periodic table. It's particularly low energy. It's just extra stable that way. Everybody's got a buddy, or all the electrons have a buddy. So this is why the noble gases don't react with anything. This is the reason that everything else is so reactive. Especially elements with electron configurations close to the noble gases. Because if they react with something, they can either gain or lose 1 electron and have a valence shell that's complete. Because they can attain noble gas electron configurations by gaining or losing or gaining a small number of electrons. Someday I'm going to restructure this class so we start with this stuff, because this is why all of the elements in the first column have +1 charges. All the elements in the second column have +2 charges. So alkali metals, like I said, are among the most reactive metals, this is column 1. Because all they have to do is lose 1 electron, and then they have a full valence shell as their highest energy level. And so that's why they form +1 cations. Because if, let's use sodium, so again, Na has 11 protons, and when it's neutral, it also has 11 electrons. If it loses 1 electron, then we'll have Na plus, because it'll still have 11 protons, but only 10 electrons. So each proton has a positive charge, each electron has a negative charge. If we have 1 more proton than we do electrons, +1 charge. So everything in the first column has a +1 charge because it loses 1 electron to be like a noble gas. This trend continues. So the alkaline earth metals, again, this is the second column, group 2A, all have electron configurations of Ns2, N being whatever row they're in. They lose 2 electrons to be like the nearest noble gas, and they all form 2+ charges. So if we look at a periodic table, so this is where you look at the nearest noble gas. So if we say, take magnesium, for example, it has, well, its valence electrons are 3s2, but it would rather have the same electron configuration as neon. And if it loses its 1 and 2s2 electrons, then it does have that electron configuration. But now it has 2 more protons than it does electrons, so it has a 2+ charge. And that is for this entire column. They all react that way, so that they can all have, so they can each have a full valence shell as their highest energy. This also works on the other side of the periodic table with the halogens. So this is group 7A, which I had you memorize as all having 1- charges. The reason they have 1- charges is if they can gain 1 more electron, they'll have a noble gas configuration, 8 valence shell electrons, but then they'll have 1 more electron than they do protons, and hence a 1- charge. Let me actually flip over to this. All right, so what other elements have? So we covered 1, we covered 2, we covered 7. What else forms consistent charges, or only one type of charge? There's a few that we haven't talked about. Pick an element, pick a column, based on this trend. So if this has to lose 1 electron, becomes a +1. These have to lose 2 electrons, they become +2. And if these ones are halogens, gain 1 electron to become 1-, what do you think the 6A column does? They gain 2 electrons. So they're 2 electrons away from noble gases. So that's why they're a 2- charge. This even holds for things like aluminum, which is one of the sort of weirder ones that I had you memorize. But aluminum's in 3A. So if it loses 1, becomes like magnesium, loses 2, becomes like sodium, loses 3, then it's like neon. It forms a 3+ charge. And so does gallium and indium. And then zinc and cadmium lose 2 electrons each. And silver loses 1. Although the reason the silver loses 1 is a little weirder than the other ones. And then these ones gain 1, 2, 3 electrons to be like noble gases. So all of these things that form consistent charges are doing so they can have the same electron configuration as a noble gas. So that's the next slide. We have also the 6A column here. Those are our 2- elements. But nitrogen and phosphorus, again, can gain 3 more electrons, or these guys lose some number of electrons. Oh, then we jump into periodic size. All right, so basically we've covered, I do want to go through these, but we've talked about electrons and how they determine a lot of things. There are some other trends that are predicted by the number of electrons that we can see on the periodic table. One of them is atomic size. So if you think about this, I've been saying that every row, we're adding like another shell of electrons. So for every row of electrons that you add, our elements get bigger and bigger. So as you right. So as you add rows, so as you go down in rows, there's down a column. Okay, we're doing across first. So as you move across, we're not adding any more on top of what we're doing, right? That's just going down a row. So as we go from n equals 1 to n equals 2, our s orbital goes from this to 1 on top of it, gets bigger. As we're moving across, we're not adding layers on top, we're filling in the layers in between. But we're adding also more protons with every single element as we go across. So because we have more positive charge, that pulls all of the electrons closer. So for every step you make going right across the periodic table, your atom actually gets a little smaller and a little smaller and a little smaller, because rather than adding electrons in shells on the outside, we're placing them inside of the same shell. So going left to right, as we add protons, we get smaller. The atom gets smaller. Yet the size of an orbital depends on the principal quantum shell, which doesn't change as we go across. Right, that's this up here. The number of protons, though, increases, which pulls on the electrons more, causing atomic size to decrease. So I was starting with this, though. So every time you go down, you add another shell on top. So as we go left to right, we get smaller. As we go from top to bottom, they get larger. So moving down a column, the highest principal quantum number increases, and the size of an orbital increases with increasing principal quantum number. So right, n equals 1, 2, n equals 3. So this is n equals 1, gets a little bigger. Every time. So if you think about this as like you can kind of think of it like two magnets. We've got like a positive magnet on the inside and a negative magnet is the electrons on the outside. As you add bigger and bigger orbitals, they're also getting farther away from the pole and the nucleus. So there's a nice periodic table with the atomic sizes, sort of relative atomic sizes. So as we go down, which is red, as we go down, our size increases. As we go left to right, the size decreases. In my opinion, it's easier to think about these, in both ways that increase. So it's down and left is increasing. It's right and up is decreasing. Or the other way I like to think about this is helium is the smallest. Again, helium and hydrogen are a little bit weird, but helium is the smallest, cesium is the biggest. So also moving at a diagonal this way, we're getting smaller until that these two are about the same size, these are, and these are. So as you move up and to the right, you get smaller. As you move down and to the left, you get bigger. All right, so let's choose the larger atom in each of these pairs. So we've got this is lead and polonium. So it's lead and polonium. Which one's larger? Lead is larger. Because it's farther to the left. So cesium is the biggest. So lead is closer to cesium than polonium is. So lead is the biggest. What about rubidium or sodium? So rubidium and sodium. Rubidium. Again, because rubidium, and maybe this is the easiest way to think about it, is rubidium's closer to cesium. And tin or bismuth. We've got tin is here, bismuth is here. This one's a little bit trickier. Bismuth is actually bigger because going from left to right makes a very small change in the size, but adding an entire shell of electrons on top is a bigger change. So going up and down is more important rather than left to right. So fluorine and selenium. Selenium, yeah, by a long shot. Very good. So yeah, cesium is big, helium is small. Oh man. All right, we're going to finish these up. There's just 6 more slides, and it's more periodic trends like this. So another periodic trend we have is ionization energy. So that's the amount of energy it takes to remove an electron from an atom in the gaseous state. So sodium plus some amount of ionization energy removes an electron. So ionization energy increases as you move to the right. It's harder to take away an electron as you move to the right across the periodic table. And again, if you think to, remember that we just talked about how sodium actually wants to lose an electron because then it has a noble gas configuration. So removing an electron from sodium or anything on the left side of the periodic table is going to be really easy because they'd rather do that anyway. Removing an electron from anything that's closer to the right side of the periodic table is going to be very, very difficult because you're moving it farther away from being a noble gas configuration. So these are easy. These are difficult. So again, thinking about our nucleus as a positive magnet and the electrons as negative magnets. Right? If you have a magnet stuck to something, it's a lot harder to remove it than if it's already far apart. So as we're moving down, the atomic size is increasing because the electrons are getting farther and farther away from the nucleus. So if the electron's already far away from the thing that's holding it there, it gets easier and easier to remove it. So as atoms get bigger, the electrons are easier to remove. All right, so the outermost electrons are farther, easier to remove. So ionization energy and atomic size are inversely related. Big atom, easy to remove electrons. So bigger atoms have lower ionization energy. So again, we can look at this on a periodic table. And so ionization energy decreases as we go down, again, getting closer to cesium. And it's more difficult as we move across, getting closer to fluorine. All right, so which one has higher ionization energy? Magnesium or strontium? Keep these out later. Higher ionization energy, so more difficult to remove an electron. Magnesium, because magnesium's smaller. So I would remember these as the opposite of atomic, right? So magnesium is smaller, so it's going to be harder to remove. Okay, indium and tellurium. Yep. Indium is going to be more difficult, so higher ionization energy. And then for carbon or phosphorus, phosphorus is going to have the higher ionization energy because it's closer to being a noble gas. So whereas adding layers, I think, is more important for ionization energy or for atomic size, being closer to a noble gas is more important, yeah. So you're closer to being that noble gas configuration. So kind of in every way, it's the opposite of atomic size. So fluorine or sulfur? It's fluorine. All right, I believe the last one, metallic character. So metals tend to lose electrons. Those are the ones on the left side of the periodic table. While nonmetals tend to gain electrons. So moving across a period, ionization energy increases. Again, electrons are less likely to be lost in chemical reactions, but also more likely to be gained. And metals are more likely to lose electrons. So metallic character decreases as you move right across a period and increases as you move down a column in the periodic table. So it's the same as atomic size. Metallic character is the same as atomic size. So again, cesium down here, most metallic character, helium or neon, least metallic character. So tin, this or that, tin or, where's tellurium? Oh, there it is. So yeah, same trend as atomic size. So tin is larger, tin is also more metallic. And in this case, tin here is actually a metal, tellurium is a nonmetal. Now silicon or tin. It's tin again. Same trend as atomic size.
Because it's more down, right?
Yeah. So bromine or tellurium. Bromine, tellurium, tellurium. And then selenium or iodine. Yeah, iodine. Same trend. Those ones I always have to think about. I mean, have you guys used iodine in a reaction yet? I don't think so. Iodine actually kind of looks metallic.